This video is the first of a series of videos about building economic theories and their representations on a graph. Reality is complex, and in so many things in life we need to simplify that reality and come up with some sort of theory to explain it. For instance, when we drive along the road in the morning and we see an accident on the side of the road, we may often ask, how did that happen? Was that a drunken driver? Was it a pedestrian knockdown? In other words, we want to have a more simplified view of that complexity. Thinking like an economist involves both induction and deduction. Induction is a process whereby the theorist starts with the facts and then moves on to theory. Whereas deduction is a situation where you start with a theory and then try and evaluate that theory by appealing to the facts. So in an induction process, for instance, a detective will find the clues to a murder, let's say, and then go and theorize after seeing those clues and come up with a theory about who the murderer is. Deduction, on the other hand, we start with a theory about how prices are determined, and then we apply that theory to the situation we see around us. So, economists use deduction to build models, or in other words, to develop or build theories. They then will look at that theory and map out its implications and evaluate those implications and modify the theory if necessary. And then they'll go out and test whether that theory applies in the real world. And finally, they will use that theory to formulate policies. For instance, there may be a theory about how interest rates work in the economy, and they will formulate policies as regards interest rates to say, solve the problem of inflation. Okay, let's start by developing a simple theory. Build a model. In this example, we'll ask, what explains high exam scores? Now, of course, there are plenty of explanations that we could proffer to explain high exam scores for an individual student, but the most obvious one would be the number of hours of study that the student puts in. However, we would have to also acknowledge that a student's intelligence and their ability to communicate are important. Maybe good teaching would help. But sometimes students strategically guess what's in an examination, so they target their learning, and they may even cheat, and there may be some room for good luck as well. Let's capture all these elements in a simple theory. And the theory can be represented in a statement like this. Ceteris paribus, examination marks are positively related to the number of hours of study a week. The term ceteris paribus simply means all other factors remaining the same. So you remember that other than the number of hours of study a week, we had intelligence, we had good teaching, etc. And what we're assuming in this theory, or hypothesizing, is that all those factors are constant, and we're simply looking at the relationship between the number of hours of study and examination marks, and we're postulating that it's positively related. In other words, when the number of hours goes up, marks go up. And conversely, of course, when the number of hours come down, exam marks come down as well. Now notice that this is not based on fact. At this stage we have no evidence, we're simply theorizing, hypothesizing, and it's important to understand that the verification comes at a later stage. Now, economists typically will use graphs to help them explain theories. And it's important that you spend a bit of time getting to understand how to interpret graphs, because they are very common in textbooks and in articles that relate to economics. Let's put our theory on a graph. On the horizontal axis, we have the number of hours of study per week, and we call these the independent variable, because on the vertical axis we have the dependent variable, namely the final exam score. Now, let's postulate a relationship as shown by this red line. Notice that the line has a constant slope. We'll see why that's important later on. The positive slope of the line shows that more hours that students spend studying will imply higher examination marks. But notice that because we've started the line somewhere other than the origin, in other words, in this case at 20 marks, we're saying that students can gain 20 marks with zero study. So these marks will be explained by those ceteris paribus conditions, intelligence, good teaching, etc., which are not dependent, obviously, on the number of hours of study a week. Okay, the next stage is to evaluate the implications of our theory. So here's the graph again. We read the graph by saying, all right, let's just arbitrarily take 6 hours, and the graph is suggesting that a student can get 60%. Some of it is simply from those other factors, and then there's going to be a gain above that due to the number of hours of extra study. So that 6 hours will guarantee 60% on the exam. If the student does 12 hours, then our theory is suggesting that they can get full marks. Now, let's look a bit more closely at the implications of our theory. Here's the graph again. Notice that the gain in exam marks is the same for every additional hour of study. We can guess this by looking at the slope. So 6 hours of extra study gains us an extra 40%, or about 6 or 7% extra for each additional hour of study. Notice that that's now represented by the slope of this line, because it's vertical over horizontal, gives us this ratio of 40 over 60, or 40 over 6, sorry. On the other hand, another 6 hours yields exactly the same amount, an extra 40%. So the ratio, the slope, because it's constant, gives us this idea of exactly the same gain. That much extra work gives us that many extra marks. Now, is that really realistic? When we start looking at the implications of this very simple theory, we really start to question whether it's a depiction that we would believe possible in the real world. Is it possible that we get a constant return from extra hours of work?